I love this picture. It is such a good picture. It gives you an understanding of stars, astronomy, but stars. This tells you more about stars than you ever wanted to know. Now the question is, I have talked about this in the class from time to time. I want to know, by a show of hands, who knows what this is. Thank you, Howard. Yeah. How about you? No.
It's a graphic representation of the relative sizes of the stars.
But have you ever seen it before?
This picture, no.
No, okay. It's because it's about as famous could be. It's not like some picture, it's the picture. No?
You definitely showed
I know.
before,
So,
and I
so
understood it
okay.
at the time, and now
So,
I
so I just want to point out, for those of you who are watching, since currently there's a very few people in the room today because it's raining out and it's nasty. But most of the people in this room have seen this before, but only a couple people recognize it. And you know why? Because we're all getting old. And so it doesn't make any difference if I repeat this again and again, as long as I repeat it differently than the way I talked about it before. Both you and I will not be bored by what I'm about to say next, because I don't know what I'm about to say next. We'll figure it out. Okay, so well, on the way here, I learned that this beautiful chart was done by no less than a woman whose name I forgot, was responsible for why it looks like this. Of course, it's awfully pretty, and she didn't make the graphic, but she did come up with she came up with the OBAFGM, and she actually came up with the acronym that so that one could remember OBAFGM. How would you remember that? O, be a fine girl, kiss me. That's how I remember it. That's how all astronomers remember the ordering of those letters. Those letters were also put together by a woman working for slave wages at Harvard University. And her job was to classify stars. So guess what she started at? She started with A, and then went to B, and then to C, and G, and on and on and on and on, all the way up to O and beyond, perhaps. And she classified stars alphabetically according to some standard that was invented by her mentor, the professor who hired her. And that classification, from A to O, was wrong. It doesn't work. It means it's meaningless. So when she figured out what the letters, how to rearrange the stars in a meaningful way, it turned out that it came out completely ass backwards, and you get this ordering of letters. So what is the ordering of letters? Why, now that you know what these now the ordering, what is an O star? What's a B star? A, F? We're a G star. We're a G star, and that is us on this diagram. But still, what is this diagram? Now you might look at it, and the first thing you might say to it, okay, I get it. And if I asked you what you thought it was, you might say, well, clearly there's something here about the evolution of stars. Clearly, stars start off here when they're nice and big, and then after time they get smaller and smaller as they burn up their nuclear fuel, and they get it down here. You would think that this is a chart that tells you about how stars evolve. And if you thought that, well, then you'd be wrong in a good way, because that's the first way you should be wrong if you were thinking about it.
But also, isn't it a light differentiation from the blue spectrum to the red spectrum?
No, you would think, well, blue is hot, red is colder, so things start out hot, then they get colder, and you'd think that, yes.
Am I supposed to say this? Now, what this chart shows is how long stars live. And the smallest ones live the longest. And as you get bigger and bigger, there's a shorter lifespan.
Now that is absolutely true. The red stars live longest and the blue stars live shortest. But here's the question. Based upon what you're seeing on the screen, so far I haven't told you, although, if you will, I've told you this because you've been here forever, but on the other hand, it still may not be clear. If a star is here, okay, and now this is a test. This is a test. So if a star is here, where is it most likely to end up after a while?
Oh,
Would you
no.
say here?
It would be end up there.
Which way would you say it goes? Here
The,
or here? Which way would you say it goes as time goes on? Would you say it goes in this direction?
No.
Would you say it goes in this direction?
Yes.
Okay. Howard, what do you think?
My guess, because I don't know.
Right.
My guess is that it goes towards supernova, so it goes to get bigger.
Okay. So it goes this way. Okay. Give that man a cigar. Okay, because it does get bigger. It doesn't get smaller. And this line of stars has absolutely nothing to do with the evolution of stars. It has everything to do with the way stars are when they are in their infancy, meaning the time that they spend before they decide to grow up and become something else. So before they become old men and women. Before they become old, in their youth and in their teenage years and even through their adulthood, they spend their time exactly where they are. They don't move. This star stays here until it gets old, and then it does something else. Our sun will be here until it gets old, and then it will go someplace else. Now, normally when people discuss this diagram, they actually explain, to begin with, what the diagram is, so I'm going to do that, but I started last rather than first. This diagram gives you, on this scale, gives you what's clear. It's clear that this scale is about the color. Bluer, redder. That's clear. You can see that with the naked eye. And what is also true is hotter, colder. These stars are not as hot on the surface as these stars. These are blue hot, those are red hot. Blue hot is hotter than red hot. You kind of know that intuitively. Your intuition is wrong, but it's still true. Blue stars are hotter than red stars. This is how bright they are. The higher up you go, the brighter the star is. So the intrinsic brightness of the star, in other words, if these stars were all at the same distance away, these stars would be brighter and those stars would be dimmer. This scale is logarithmic. So this and this are related by the fact that this is 10,000 times brighter than this. And this is 10,000 times brighter than this is 10,000 times brighter than this. It's 10 to the 5th, 10 to the 10th. So this graph is logarithmic, and so because if you did it rather normally, the way one would tend to plot it, you'd need a piece of paper that would be miles high in order to plot this thing, because it wouldn't work. So you crunch it down. Okay. This is called the Hertzsprung-Russell Diagram, and it's named after two guys, each of whom came up with this independently, and so they both got their names on the same thing because they came up with the same idea at the same time. And the reason I'm telling you this has nothing to do with the evolution of stars. I'm not telling you this because I'm trying to tell you how stars evolve. Because if you've been paying attention, which is possible, you would know that I'm trying to tell you how to find the distance to these stars. That's what I'm trying to tell you. So I'm trying to tell you how to find the distance to these stars, and yet I'm telling you about these stars. Why? Well, let's see. I see a star in the sky. It's dim or it's bright, but I don't know how far away it is. The dim one could be close. The bright one could be far away. I have no idea. But I can look at the temperature. I can look at the color of a star. The star is blue. Oh, it's blue. And this is shades of blue, if you will. So if I'm really good at figuring out what shade of blue it is, I can say, oh, this is such and such a shade of blue. And they can actually figure out the shade of blue absolutely perfectly. I mean, they can divide the shade of blue here. This B can be divided into 10, B1, B2, B3, B4. We are a G2 star, a G2V star. Our color is G2V. So every one of these stars has a really very well-defined color. So when you know the very well-defined color, you just look on this diagram and you go, I see. Well, that's so bright, but it doesn't look that bright. It looks pretty dim. So it must be far away. And this one, over here, I see it and it looks bright in the sky, but I can see that it's a dim star. So something that's bright and red is intrinsically dim, so it must be really close. So if I can figure out how far, if I can do one experiment where I could get this main sequence and measure the distance to a group of main sequence stars, I have figured out how to figure out how far away stars are. It's just amazing. One little diagram that everybody agrees is really important is the one little diagram that gets us from A to B to C and helps us jump among the stars almost to the end of our galaxy. Yes?
Partisan question. Why is it that Hertzsprung-Russell get their names attached, but the lady who got slave wages doesn't get her name attached anywhere, and it's her picture?
Because it's not her picture. What she did is she said, the order is incorrect. The order is O, B, A, F, G, A. But she did not then make the next leap to draw a diagram with this axis versus that axis. That was Hertzsprung and Russell. She got this axis right, but she didn't do this axis. She got color temperature right, but she didn't get luminosity at all. So that's why she didn't get her name on it.
Punishment because she was female.
Yeah, no, it's punishment because she was early. She was early. The people these guys, used her work a couple of years later, but not a year later, but a couple of years later, they used her work to figure out the rest of it. Now the thing is, there's a problem. Yes?
I have a question. So now you know that the blue star, the dim blue star, is far away.
Right.
How do you determine the distance from Earth that it is in terms of light years? How do you determine
Okay,
that?
so
That's parallax.
parallax. So that you do that this way. So what you do, see, there is a series of stars in the sky called the Pleiades. The Pleiades looks something like a Big Dipper. You can see it with the naked eye, especially in the summer. You can literally look up and you can see this small little itty bitty Big Dipper, just barely visible to your eye. You can see the stars. It's the same formation that's found on the Subaru emblem. Subaru means Pleiades. That's what you see. You can look up with a telescope, and instead of seeing 7 stars, you see thousands of stars with the telescope. You see thousands of stars, and those thousands of stars How did they get there? Why are there thousands of stars here? Because there was an event that took place millions of years ago, hundreds of millions of years ago, when these stars all were formed at the same time in a molecular cloud. There's a cloud of gas out there. There are clouds of gas out there all over the place. The universe is filled with clouds of gas. There's more gas than there are stars. More gas than there are stars. And this cloud of gas, for some reason, perhaps a nearby supernova went boom and pushed it a little bit, so it got scrunched enough so it could say, ooh, I could start to make stars. And so little stars started popping out of the gas almost at the same time. Within, say, 1 million years of one another, you formed probably 1,000 stars, all at the same age and all at the same distance.
At the same distance from what?
From us.
But
This cloud, wherever it is, was formed at the same time and at the same distance from us.
But stars are millions of miles away from each other. So
These are light years. These are light years away from one another.
Okay, so how?
But this is thousands of light years away from us.
Right, but that's not the same. If I'm in Chicago and somebody else is in Scarsdale, that's not the same distance from somebody in Florida. There's a difference.
No, every one of you on this earth is a member of the Pleiades.
Okay.
But the distance that we're talking about is relative. If we would be at the distance of the sun, looking at the various cities on the earth, and I would say that all the cities on the earth are at the same distance from the sun, and you wouldn't have any problem with that.
Because it's on the earth.
Because it's on the earth. The earth is a little pitty pipsqueak, and it's 93 million miles away from the sun. So from the sun, they're all the same distance, and that's what I'm saying. Even though they're light years apart, they're still at the same distance. Okay. And then the Pleiades is something that, although it's far away, thousands of light years, still the Earth goes around the sun, and sometimes you can see the Pleiades over there, and then sometimes when you're on the other side of the sun, the Pleiades are over there, and so the Pleiades move in the sky as the Earth goes around the sun. The Pleiades moves against the background stars, just like nearby objects when you're in a car or a train move against the background object. Can I ask you, as a child, were any of you aware of the fact that when you're in a train or a car, the foreground objects move quickly and the background objects move slowly?
Yes.
Were you aware? Raise your hand if you were aware of it as a child. Yeah, okay. Yeah, so we have half the class. More than half the class. I was aware of it as a child. The interesting thing is that I didn't become aware of the answer until I heard the word parallax, which occurred way into, after high school, probably somewhere into college before I heard the word parallax. And that explains it. But somehow it still doesn't satisfy my child brain. I'm still interested in why those things that are nearby move so quickly and the things in the background seem to not move at all. Still doesn't satisfy my child brain. I'd like an explanation that you could give to a child that would explain why foreground objects like the Pleiades move in relation to the background objects, and to work an explanation that I could say to a 5-year-old, because I'm sure that's what I was more or less when I had the question. But anyway, so the Pleiades is at a certain distance. So you know how far away it is. They're all the same age. So when you plot the Pleiades on a diagram like that, you get, well, you actually don't get this. You don't get this. That looks like that, but remember that picture over there? This picture has all those other things that don't seem to be on the line. Those things are the main sequence, but this is the main sequence the way it looks when in the infancy of these stars. These stars are all very young. This one's young, and it's the same age as this one. But what happens to this one is a different story than what happens to this one. These stars, the red ones down here, will stay here, not doing anything interesting for 1 trillion years. Not 1 billion years, 1 trillion years. These stars are good. They're staying there for 1 trillion years. These stars have other ambitions. This one in particular, our sun, I'm doing the Pleiades, but this is any cluster of stars, and our sun was born in a cluster of stars. Our sun was clearly born in a cluster of stars. The birth cluster of our sun has dissipated. And when people talk about being lonely, there are people who literally talk about wondering if they could find some of the birth brothers and sisters of our sun. And people are out there looking to see if they can find other stars that were born at the same time as our sun, but it's probably a very difficult task.
Sibling sons.
Sibling sons. But all those in the Pleiades were born at the same time. Our sun, however, has other plans. It's going to stay where it is, more or less, for 5 billion years more. It's been there for 5 billion. It will stay there for 5 billion. But as the years, the billions of years wear on, our sun is going to leave the main sequence. It's headed in that direction. It's already headed in that direction. It's hardly got there. But it's headed up here. It's headed up there. Wait, yes.
Since all of them are moving.
No, forget
they're
moving.
all
No. This is not moving except on this diagram. And try to imagine, for the sake of this argument, that these stars remain in their little cluster forever. So they're not moving very far. They're all hanging together. Though in truth there's another story entirely in which they do eventually leave home. But that's not this. This is not a spatial diagram. This is not a spatial diagram. It is a diagram of luminosity or brightness versus temperature or color. It has nothing to do with space. There's no dimension of space in this picture. It's only brightness versus temperature. So when I say move, it doesn't mean move in space. It means move on this diagram.
And luminosity then.
Right.
Okay.
So the luminosity increases over time. Yes?
Basically, you're saying that all of this group of stars formed in a cloud around the same time, but there's a difference between the luminosity of the ones within it.
Yes.
Do we know what ingredients there are that make some brighter and some dimmer, or different temperatures or different luminosity? In other words,
Yes.
if there's a group of stars.
Do we know what makes some brighter and some dimmer?
Age.
Do we know what? No, age is the wrong answer. Thank you very much for the wrong answer. That is a terrific wrong answer. That is one of the best wrong answers I've ever gotten. Okay? Okay. Really, you have to appreciate wrong answers. They are,
Is that a compliment to her?
of course, it's a compliment to you, Barbara, that you asked the question. It's a compliment to Marion that she guessed wrong. It's the best, it's not about age. They're the same. Yes.
Does size have anything to do with it?
Size. The question is what, but Barbara's question is why are they different sizes? Okay. The why are the stars different sizes?
No,
Because
she didn't have size.
Different
What?
luminosity.
Different luminosity.
and listen different sizes and different luminosities. Okay.
And are all
Bigger
those that are
big-
similar in the same part.
Bigger stars here, these ones, forget these outliers. These bigger stars are more luminous. Bigger, heavier, more massive stars are more luminous. Smaller stars are less luminous. That is simply true. Why? I think, Barbara, you asked the question, why are some of them just bigger and more luminous to begin with? In their cradle, why are there some eggs that are bigger and some eggs that are smaller in the same cradle? And the reason I love the question and I love your wrong answer is because that literally brings up the entire topic of stellar evolution from birth to death. And we are not doing stellar evolution in this lecture because I'm trying to do stellar distances. See, so I'm not answering the questions well enough, but I will explain what it is. Barbara, your question, Mary.
And my other part of the question
Yes.
was, for the things of one size, let's say they're all within a square.
Let's say they're all within a
The
square.
smaller ones form on the right side and all of the bigger ones on the left side, or is everything mixed up within this?
Why are certain, in the square, if you will, where the things, are the big ones here and the little ones here? Why are there big ones and little ones? And does it have anything to do with where they are?
Right.
Okay, now Barbara, I have to tell you, this is yet another one of your great questions. Okay, because there is every reason to believe that where they are has everything to do with how big they are. Isn't that interesting? Where they are. Okay, let's imagine that you've got two clumps of stars. This clump is the same size as this clump. And they're about to make, this is gas, they're about to make stars, each of them. Because the big gas cloud that's light years across, tens and 100 light years across, has come together and is forming little stars, and these things are now maybe a light year across each of these clouds. And each of these clouds are now condensing to make a star. And it's going to take them maybe 10 million years to do it. This one gets the job done 2 weeks before this one. 2 weeks, maybe a million years before this one. But these things, a million years in these conversations is no time at all. So, but I say 2 weeks because literally what happens, it's in a flash of time, this one becomes a big blue massive star, and this one, which has every intention to become a big blue massive star, is too close to this one. This one ignited and is suddenly incredibly luminous. And this one is just a ball of gas. This one sends its intense ultraviolet rays everywhere in space. And guess who happens to be standing by minding its own business? This other star, which was going to go just as big. But because this star ignited, it blows off and ionizes all the gas that's around that star and eliminates most of the gas that was going to form that big star. And that big star ends up becoming a little itty bitty star instead. So the proximity to a forming blue giant it turns you into a small dwarf star. So that's to answer your question.
So the first one.
The first ones kill the other ones, and I have in part of the lectures that I will do, I have hundreds of pictures of this going on. This is so spectacular that the favorite things that astronomers like to photograph is this process in its works. We have hundreds, maybe even thousands of stars that show this process ongoing. It is beautiful. And we will get there eventually. If you keep coming, we're going to get there. I'm going to do her. Yes?
But if this process, say, takes so many millions of years, then aren't the bigger ones kind of older? Because you said they formed first.
Within a couple of weeks. I said a couple of weeks to give you a
And
sense.
you said it's really millions of years.
Yeah, but millions of years. Remember, we got billions of years to work with.
So relatively speaking, they formed at the same time.
At the same time. They did form at the same time. So to cue your mental image to that, I said a couple of weeks, but it's really could be a million years, but it's still the
That's
same
not
time. Same time.
Okay.
Yes.
Analogizing it perhaps to gestation, when there's a child, two zygotes in the mother, when one is taking more of the nutrients, even though they're twins, sometimes the twin gets more and more, less and less of the nutrients, and the twin, the one that has started getting more of the nutrients, gets more important, more big, more significantly rounded out, and the other one gets scrawnier.
No,
And
it's
when
mo- it's
born,
more it's
really
more
scrawny.
it's not like that, because that, as an analogy, one is taking from the other. In this case, one is actually destroying the other. In other words, if you want to make an analogy,
That's the same.
find an analogy in which two animals born at the same time, and there are lots of examples like this. Two animals born at the same time, the one that's born first kills the one that's born second. In the bird kingdom, there's lots of examples of that. I don't know particularly what bird, but some birds absolutely kill. So there's only one egg left in the nest, for the mother to raise, and so the first one kills it. The mother does this. She lays 2 eggs as insurance, but she can only raise 1. So the first one that comes out kills the one that didn't come out yet. That's one of the laws of nature for that species of bird. Well, that's not, again, it's better an analogy, but it's not a good analogy anyway. What's happened is, this is not fraternal assassination. This is just one star heaving, doing what it does best, which is be luminous, and the other star doesn't get a chance to form as well. Okay. But there's a way that the little star gets revenge on the big star, because the big star is so big that it burns its nuclear fuel very quickly. Very quickly. In terms of, if I gave you the 2-week analogy, if you will, if the next star forms 2 weeks later, and if I use that 2-week analogy, I would say about a month later the big star dies.
Oh.
In truth, it's 10 million years. But these stars here don't live more than 1 million to 10 million years. The bigger the star, the shorter it lives. These stars, some of them, actually, Howard, some of those stars do blow up. The very big ones do blow up. The other ones, they don't blow up. They just do some nasty things that leave them not as a supernova, but as some sort of stunted version of themselves. They still blow up, but they don't blow up to become supernovas. They just blow up. And some of the other ones, well, they don't blow up as quickly. And if you're talking about blowing up, our sun is never going to blow up, but it's certainly going to do some nasty, nasty stuff that is about tantamount to blowing up. Our sun, for the next 5 billion years, more or less, will be right here on this HR diagram. And then our sun is going over here. Our sun is headed in this direction on the HR diagram. Our sun is headed in this direction on the HR diagram towards the giants. You've heard that our sun will one day become a giant star. It will. It will get so big that it perhaps will get this big. Now, this is a log scale. So this is 10,000 times brighter than our sun, which is 1. Our sun is 1. This is Betelgeuse. That's 10,000 times brighter. Our sun will become like Betelgeuse in the future. Not blowing up yet, but it will become so big that it will envelop Mercury, Venus, and the Earth. Will all be inside of our sun, as our sun still has not blown up, but has gotten awfully big and very, very bright. And it's so bright that it's literally radiating away all its heat. It's using up its energy very fast now. Yes?
So Mars will become a Riviera.
Mars will definitely become a Riviera. By that time, you don't have to terraform Mars, but it might become too hot to live on. That's why when they did 2001, Europa was the planet that Arthur C. Clarke gave to the planet, saying you do not land on Europa, because Europa is likely to be the place that is good to be when the sun becomes as big as Betelgeuse.
But Europa is a moon.
Yes,
It's not a planet.
it's a good place. There, I believe, I believe that if you are inventing life on other planets, your best place to invent it is on moons. And the places that we have many places on the solar system to look for life. Not Mars. Mars is a pretty poor place to look. Because if we find it, and it looks like it's got DNA, it will be meaningless, because we know that Earth and Mars interchange meteorites all the time. So we know that Mars could have some of our DNA, and we could have some of its. So if we both have DNA, and we discover life on Mars, it'll be the most significant disappointment in the history of biology, because they won't prove anything. But if they find life on Europa, if it has DNA, nobody's going to claim it came from Earth. So it's a big deal, right? So, but I think they will find life on Europa, possibly.
What's going to happen to the Earth as the sun moves?
Burned to a crisp, as they say. Completely subsumed by the sun and disappears. Gone forever.
So that explains global warming?
No, it doesn't. No, it doesn't. In fact, global warming is its own problematic story here. And then, so the sun does this, okay? Then, but the sun isn't finished. Then it does one more thing. And then it blows up. The sun sheds its outer layers. It goes, I don't need this anymore. Why would I want to be so big? I don't need this anymore. And it blows off its outer layers. And there are beautiful pictures, hundreds of them. I have hundreds of pictures to show you, of stars like our sun blowing off their outer layers. And they become what's called Planetary Nebula, a misnamed word describing what happens when a giant star blows off its atmosphere. Yes?
How can they take pictures of that if it's hundreds of millions of years ago?
They have hundreds of millions of stars to take pictures of. So that star,
Think of a photograph as being a discrete image.
yeah, so everywhere you look in the sky, you're looking back in time. But that's somewhat irrelevant. Every place you look in the sky, it's a different thing. This is older, this is younger. That's more to the point, not back in time. This formed more recently than that one did, in terms of real time, whatever the time on their clocks are and our clocks. They have the same clocks as we do. If you ask them what time it is on their clock, they will say, well, it's the same. It'll take 100 million years for that information to get to us. So it'll be 100 million years delayed, but still, our clocks and their clocks are the same clocks. They tell the same time. And if I ask, and right now, on that star, something's going on, and it's a younger star. That star over there, something's going on. It's an older star. So two stars are having different things going on, and all we have to do is look in the sky and see, that's interesting. That's interesting because it's different from this. And then, of course, there's the time that the light took to get to us, and that also makes a difference in terms of, maybe this one's younger, but it's further away, so it's going to take a longer time. So it's going to reach us later than this one. All those things. Nevertheless, the sky is a coloring book full of images of anything you want. Old stars, new stars, bright stars, dim stars. It's everywhere. You just need to take a look at a lot of them, and you'll find everything going on, everything. And so this becomes that. These giant stars become white dwarf stars, so dim they're invisible to the naked eye. We don't see a single white dwarf with the naked eye in the sky. Yes?
Since the sun will be factorially larger, logarithmically larger,
Yeah.
but it doesn't inherit bunches of money from its father, how does it stay integral to itself? Because the sun has this amount of material and it's burning like mad, and then suddenly it becomes much, much larger. That material is then thin and thready and
Yes.
hardly
Yes.
any material, and lots of space between all the materials.
Yes, but nevertheless, gravity is saying, "Stay here, stay with me. You belong to me. You're allowed to hang out further from the center. You can be further out, but you're still staying with
Part
me.
of me, okay.
You're still part of me. But with the time for the gases that make up the outer envelope of the star to leave is when the star itself produces explosions that blow off the outer layer. So those explosions are called nova, not supernova, but nova explosions, blow off the outer layers of the giant stars, giving them more energy to leave the gravitational field of the sun forever. So there is these explosions. So most stars do have, that grow to be giants, do have explosions on the surface, but they don't blow away. They just blow off their outer layers. And that's what happens to the poor stars. But they remain. So they go. So this becomes that, and this. These never do that. These will take 1 trillion years to do that. These will take 500 million, a billion years. This will take 5 billion years to do that. And when it does that, it goes there and goes there. So if you're looking up in the sky and you're trying to figure out how far away things are, you've got this little bitty problem that I told you that this main sequence of stars will tell you how far away the things are. But it doesn't. Because there's all these other junk things around that confuse the issue. This is also red. This is as red as this. In fact, see, they put it here. But it's 1,000, 10,000 times brighter than this. And yet it's in the same color. So you got to deal with the fact that you have some of these to confuse the issue. And there's a way to resolve what that is. But I think I should leave that. Or should I not? Maybe I shouldn't leave it. Maybe I should explain it. But in order to explain it, the problem with explaining how I can figure out that that's a supergiant and that's a dwarf really will take me 20 minutes to do it well. So I don't think I'll do it this time. So I'll just leave it to the questions.
And you're forgetting the red behind. There's an even greater one that's on the top margin
Yes.
of the picture.
Yes, that's a very, very big one. And
Very big.
And yet you can't tell easily that it's not one of the itty bitty ones. So you might confuse, if you're trying to do distance measurement, you've got a red star you're looking at, and you don't know how far away it is, and you're trying to figure out how far away it is based upon its brightness, you can confuse a red dwarf with a red supergiant, right? I mean, conceivably. So you have to be able to distinguish between the two. And there's no obvious way to do that in this diagram. So what you need is more data. And that's what I'll show you next time. But I'll tell you the answer, just so it'll get you started. The answer is, this is what this cluster looks like. This, let's say Pleiades, looks like this, with all the confusing stuff in there. Okay? You look at a different cluster, and it doesn't, this main sequence is the same, but right about here, there's no more of these. These have all disappeared. They've all gone up to here. So where the main sequence stops tells you how old the cluster is, because these start breaking away, and after billions of years, then these start breaking away, right? And 5 billion years from now, this will break away, and they'll break away towards that. So all you have to do is figure out, oh, I have a cluster that has this broken away, so I know that, I can see these are clearly belong there, because I put them, I know what the distance is. As soon as I know one of these stars, I can figure out how far away it is, and then I can figure out the rest. I need the stars in the cluster all together at the same distance, and then I can see the red bright ones are at the same distance as the red dim ones, but this one's bright, so it must be a supergiant. It's because I'm using the cluster as the rule of thumb. The cluster says, I'm all at the same distance, deal with it. Then big and bright means supergiant, dim and red means red dwarf. And we're a dwarf. Yes?
Just remind me, what triggers the smaller sun, let's say, to turn into a giant?
I don't have to remind you. I didn't say it.
Oh, you didn't say. Okay.
Right. Yeah. Though it's not obvious, but I can tell you the obvious part. You run out of fuel. Hydrogen is being burned into helium. When the hydrogen is burned into helium and then all the hydrogen is used up, which in our case will take another 5 billion years, then the star has got a problem. It can't support the outer layers of the star because there's no heat being generated to push the outer layers out. There's no light being generated. So the outer layers start to come falling in to say, if you're not supporting me, I'm coming in. As soon as it comes in, falls in, the falling in heats up the center of the star so hot that the helium is able to smash into other helium atoms and produce, say, carbon. And now you're burning helium. So now the star is burning its secondary fuel. So the center of the star is compacted, and as it turns out, this is how I explain it, as it turns out, the outer layers expand. Okay, so the inside gets smaller and the outside gets bigger. So there is a trigger, but I didn't explain why the outside gets bigger. Okay, so, because I don't remember to explain why the outside got bigger. If I did, I would. Yeah, yes.
Is there not a gap?
What?
Is there not then a gap? This guy is going there, this guy is going there, one is condensed, one is expanding. That means there's a big area of gap.
Well, you would think so, but no. Logically, try to think of it as it's a continuous surface. Some part is denser, it's continuous. Denser, less dense, less dense, less dense. There's never a middle that's not, because there couldn't be a gap. Yes?
Do we know if every initial cloud that forms all of these clusters,
Yes?
do we think that every one is basically composed of the same material, perhaps in different amounts, so that we can speculate that every cluster that we see is made of the same stuff?
See,
Do we see something that looks like there's something different?
Okay, so Barbara, I keep thinking. So do different clusters seem to be made of different stuff, right? So for those of you who have not been, watching, you need to know that I did not plant Barbara in the class. I didn't give her a set of questions to ask, but it turns out that whenever Barbara asks a question, she asks the very best questions that I could possibly ever want.
And you answer it.
Right.
That's question.
So is one cloud different from another? Is basically your question.
Yes.
And the answer is yes, indeedy, they are different from one another. In fact, that is a big deal. This main sequence is only for a particular kind of cluster, and other clusters look slightly different than this exact main sequence because they're made of different stuff. What? They're made of different stuff? How could that be? Because the universe has a history. If you walk down the street, occasionally you step in schmutz. Occasionally you have a nice bright sidewalk. Sometimes they didn't clean the sidewalk and there's garbage everywhere. The universe is like that. There is no street cleaning crew. So if a star blows up, nobody cleans up after it. It just lays there. But when the star blows up, it leaves behind a lot of schmutz, a lot of debris. That debris is called, in astronomical terms, metals. The word metal in astronomy is one of the worst and best words I love. It means anything that isn't hydrogen and helium is called a metal. Anything that isn't hydrogen and helium is a metal. So that means carbon, nitrogen, oxygen are all called metals as far as the astronomer is concerned. And the degree of, and this is a great word, if you haven't heard it before, you should include it in your vocabulary. The degree of metallicity of stars varies throughout the universe. The metallicity of our sun is quite high as compared to other stars. Thank the heavens for that, because if it didn't have a high metallicity, then we, who are made up of the only thing in our body that isn't, quote, a metal as far as astronomers are concerned is hydrogen, which makes up all the water in our body. But otherwise, the DNA has no hydrogen in it, particularly. I mean, in the four letters of the DNA alphabet. We're made up of the metals that formed in the side of stars, and that star and the Earth is made up of the metals that were formed in the side of a supernova, and our sun has those metals in it as well. The metallicity of our Earth, well, the metallicity of Jupiter, which more or less has the same stuff that the sun was made of, is by hypothesis alone to be assumed to be the same as the sun. The sun and Jupiter exactly the same gases, same metallicity. We have lost the hydrogen that used to surround us, perhaps. So there's no hydrogen to add to our atmosphere. So we're mostly just the metals. Some stars have very low metallicity, and when they make planets, you can be sure those are going to be very inferior planets, because they're not going to have any hard things to land a ship and sail across the ocean on. You need these metals. So some stars are young, and some stars are young and some stars are old, but it makes a difference what they were formed out of. And if you are formed out of metal-rich stars, you're called a population 1 star. And if you're formed out of stars that had almost no metals, you're called a population 2 star. If you will, 2 is older than 1. So population 2 stars were formed many years ago when the universe was young and there were very few metals. And population 1 stars were formed just fairly recently. That means in the last 5 billion years. And they have a higher metallicity. But you got to be in the right place at the right time, because if you are in the wrong place in our galaxy, the metallicity changes as you go around the galaxy. So the galaxy has good places and bad places to form life in. If you're too close, if you're too far out in the galaxy, there's not enough metals out there to form good planets. So you better be in a place where the stars have good metallicity, which is the central part of the galaxy that we live in, so we can be formed as a life form and raise our hands. Yes, again.
That's a contradiction of you told us that our galaxy, the Milky Way, is a spiral disk.
Yes.
And that we are located on the outer spiral.
No, galaxy is 100,000 light years across, okay, or 50,000 from the center, if you will, to the more or less edge. Although it's really 3 times bigger than that, but 100,000 from center to edge, and we're here. We're in the mid between the furthest and the nearest. We're right where the metallicity is just right. If we're too close, we're not in the outer spiral. No, we're in one of the inner spirals. Yes.
But all have hydrogen and helium.
Yes, but we need those metals, and those metals are made in supernovas, and those supernovas need to fill the nearby galaxy with metals so that we can form them when we form our stars. Those stars are formed early. They blew up. Some of these big stars blew up. They formed the metals, and sometimes even twice and 3 times. We think that our sun is a 3rd generation star, meaning that the metals in our sun came not from one supernova explosion, but from 2 or maybe even 3 supernova that gave us the degree of metals that we have in the sun and on the Earth. Yes?
So why wouldn't it be easy to hypothesize a planet similar to ours with the metallicity that we have that exists? And you said a few weeks ago that it's very rare to find a planet like ours. But it seems to me if the metallicity is right, even if it's light years away,
No. By the way, I want to change it. A planet doesn't have metallicity. The star does. The planet inherits the metals, but it doesn't have. Yes. I would say that of the stars in our galaxy, which is number 400 billion, half of them have the right metallicity. So it's not. So metallicity is a contributing factor,
Not determinative.
but not determinative. There's a lot of other factors that determine whether or not a planet is suitable for people like us to visit, including a good nightlife on Saturday night. Yes, yes.
Does anybody ever ask the question that since we only see 4% of everything, 4%,
Yeah,
that 96% of the universe is a mystery to us.
right. But Howard, staying on topic, that
But I'm trying to, that in the dark matter, that we call dark matter, things are happening that we have no idea of.
But I'll tell you one thing I can tell you about. Dark matter has nothing to do, as far as we know, with anything you see on the screen. Dark matter, when it's present, is present at the level of galaxies, not at the level of stars. We have a solar system out there, right, really close by. It's in the we're solar system. You think we could find some dark matter? It should be here. Should be in the sun. There should be. There probably is. But think of it this way: the space between the stars is so big. So the dark matter is in the space between the stars. Yes, there's some dark matter in the sun, but the sun is small compared to the space between it and the nearest star. So there's 4 light years worth of space to fill before you meet the next star. So that all that dark matter is everywhere but in the star. It has nothing to do with the formation of the star. That's why I'm always dismissing the conversation of dark matter, because it only comes up at the galactic level, and at the galactic level I've hardly discussed anything in this class. So that should be it for the class today. Okay? So we'll see you in the new year. Okay?
Happy New
Oh,
Year.
and the attendance sheet. Please, I always forget it. Please.
What about the Gemini meteor shower? We didn't mention that, or did
Because it's
you?
on the.
No, I know, but it was this week.
Oh, I always don't pay attention to that.
You don't pay attention
No,
to it?
I don't. I don't look up.
He doesn't look up.
Oh,
Don't look
because
up.
if you go on the roof, you'll find it.
I don't look up.
I see.
You can't see them anyway, it's too cloudy, too
No, you
blue.
can if you're around a very dark, a bunch of
So difficult.
apartments.